In this video, we're going to use our knowledge of exponential equations and logarithms in order to solve exponential equations. Now, the first of the two strategies we're going to look at for solving exponential equations utilizes this idea of the property of equality. And in math terms, the property of equality states that if b is a positive real number other than 1, then b to the power of x equals b to the power of y, if and only if x equals y. Which should make sense. Basically what this is saying is if we have 3 to the power of x and we have 3 to the power of 2, well, these two situations have the same base. And so the only value for x would be 2. Because if we kept going with this, we would have 3 to the power of x equals 9, and we would know x has to be 2. So basically what this is saying is if you have common bases, you can set exponents equal to each other, which is a really nice trick. So basically, in any situation that we might have, so say we had something like 5 to the power of, x plus 1 equals 25 to the power of 2. Well, realistically here, while these don't have the same base right now, I can rewrite 25 to be 5 squared. So this situation can become 5 to the power of, we multiply our powers, so 4. And then from here, we could set our two exponents equal, so x plus 1 equals 4. You subtract your 1, and you find x is 3. If we can get them to have the same base, we can then set exponents equal. So that's going to be our goal with this first strategy. Our goal is to get these two exponents on different sides of the equation to have the same base, so we can then set their exponents equal and solve for the missing variable value that's contained inside of the problem. So let's jump in and try a couple of examples. This first example, what I notice is we already have identical bases. When we have the same base, we know that the exponents need to be equal. So we can set them equal to each other. So in this case, 2x minus 5 equals 6x minus 8, and then we can solve. So this should be as simple as, you subtract 2x from each side, you add 8 to each side, so we end up with 3 equals 4x, divide by 4, and x is equal to 3/4. Really is as simple as that. If they have a common base, you can set their exponents equal. Now, if we look at this second example here, what I notice is that we do not have common bases here. We have a base of 4, and we have a base of 64, which isn't quite the same. But what I know about 64 is 64 can be rewritten into a base of 4, because 64 is 4 to the power of 3. So I'm going to rewrite 63 as 4 to the power of 3 here. Now, I want to simplify that right-hand side a little bit, so I'm going to take my powers, multiply the 3 by both of those. So I end up with 4 to the power of 3x minus 5 equals 4 to the power of 6x minus 24. Now, because I have these common bases here, I can now set their exponents equal to each other. So this would become 3x minus 5 equals 6x minus 24. We would then need to add the 24 over, subtract the 3x over. So we end up with 19 equals 3x, divide by 3, and x is equal to 19 over 3. And you can find what that is as a decimal too, but you can leave it as a fraction. So the big key idea here is, can you get a common base? You need to rewrite it with a common base and then, alter the exponent a little bit from doing so in order to then set the exponents equal and solve. So now let's take a look at two more examples that are a little bit more involved. This one down here, I notice I have 1 over 125. And I also notice my other base is 5. If I want to use this base equality property, where if the bases are the same, then the exponents must be set equal and be the same, we need to get these to be matching. Now, 5 doesn't condense down much smaller, but I do know that 1 over 125 can be rewritten as 1 over 5 to the third. Then I also know that I can move this exponent up, and it would become 5 to the power of negative 3. So what I can do here is I can rewrite 1/25 as 5 to the power of negative 3. So this is much closer now to having the same base, so I can set those exponents equal. Now I do need to simplify my exponent here a little bit, so I'm going to distribute out that negative 3. So this becomes 5 to the power of negative 6 plus 3 and 5 to the power of x plus 3. Now, because I have rewritten this so that we have a common base, I can set their exponents equal to each other. So I have x plus 3 is equal to negative 6 plus 3. Well, if I start, I'm going to add 6x to each side, subtract the 3 from each side, so I end up with 7x is equal to 0. Divide both sides by 7, and I find an x value of 0 will make this particular equation true. Finally, in this fourth example, what I notice is I have an interesting situation here. I have 100 on the left-hand side, and I have 1/10, which is 1 over 10 to the power of 1 on the right-hand side. Because they both kind of are 10, 100, whatever, I'm going to try to rewrite them as bases of 10, but not in the denominator. I want the 10 up in the numerator. So let's start with the 100. I'm going to rewrite the 100 to be 10 squared, which I can then rewrite this 2 times 4x is 10 to the power of 8x. Now this I want to be up in the numerator, so it can be corresponding with that base of 10 on the left-hand side. So this is going to become 10 to the power of negative 1, and then 3x plus 2. So I've got common bases of 10 on both sides. I just want to clean this up a little bit, so I'm going to distribute that negative 1. So we leave the left-hand side alone, and we have 10 to the power of negative 3x minus 2. Now, because we have common bases, we can set the exponents equal to each other. So we have 8x is equal to negative 3x minus 2. I can add the 3x to each side. So I get 11x equals negative 2. Divide by 11. My answer ends up being x equals negative 2 over 11. So in each of these cases, our goal was to rewrite the equation so that we had a common base on each side, so we could then find what the exponents were for those common bases. And once we had those exponents, because we had common bases, we could set all of those exponents equal to each other. Now, something to note is that you can take all of these answers, so 3/4, 19/3, 0, and negative 2/11, and if you plug them back in and you substitute them in place of x in your original equation, they will make that original equation true.